Good morning. We have a midterm coming up. We have our first midterm coming up very soon. We are in review mode. We've covered chapters 1 through 6. We've been pretty thorough with the lectures, with the homeworks. So let's take a look at these set of problems. So the set of problems that I have here, I've got a couple of these. They're actually midterms from previous semesters. So this is the format: 4 questions, individual parts A, B, C, D, however many individual parts. So let's go ahead and take a look at these as a review, and the midterm we're having will have the same format. So 4 questions with individual parts on those questions. So the first question we've got here, it says that we've got a couple of stones being dropped from a tall building. We drop one, and then we wait 1 second and drop the other one. So, 1 second delay. And then it says when the second stone is being dropped, how far has the first stone fallen? So how much of a head start did that first stone get? We're trying to drop one, and then drop another one, and ask what happens to, the separation between these two stones. So, I got a diagram here. Here is the first one being dropped. Here is the second one being dropped. And what we can do, this is an example of constant acceleration due to a gravitational field. And so we can use Earth's gravitational field to help us determine how far this thing will have dropped. Now what we're told in part A is that 1 second has gone by. So I'm bringing in an equation that we've used several times now, I guess. So this is kind of a chapter 2 question. And it says that if I have uniform acceleration from rest, the distance that we drop can be determined 1/2 acceleration t squared. This is 1/2. Here is the acceleration due to Earth's gravitational field. And here is 1 second going by, and it says 4.9 meters. So let's see, 1 meter is like this. So, 4.9 of those, about 5 meters that this thing has dropped. So just in 1 second, right? So I let go, and after 1 second, this first stone will have dropped 5 meters. That's not quite a couple of floors on the building, but it's a good distance. Now in part B, what they're saying is, okay, what happens by the time the first stone is going 25 meters per second? How much separation will there be between the two stones? So in part B, we're bringing in more equations for constant acceleration. What we're saying here is that we can take the velocity as a function of time equation and solve that for time. So the amount of time it's going to take for stone number 1 to reach 25 meters per second, well, we can calculate that as v over the acceleration. So that's 25 meters per second divided by 9.8. It's going to take a little more than 2.5 seconds, so 2.55 seconds, and that first stone will be traveling at 25 meters per second. Now in these problems we know we're ignoring air resistance, and so we're thinking of these stones as they're dense objects, and we're thinking of them as large enough that the air resistance effect will be small. So 2.55 seconds, so once that much time has passed, we can go back and use individual distance formulas for each one of the stones. Now I'm writing down 1/2 gt squared for each of these. Now for stone 1, it's been falling for 2.55 seconds. I'm putting that into the equation, and it says it will have dropped, I probably kept more sig figs than I needed, 31.9 meters. Okay, so it's dropped a good distance at this point, 30.9 meters, and it's been falling for a little over 2.5 seconds. Now remember, the second stone is going to be dropped 1 second later, exactly, I guess. And so for the second stone, it's only been falling 1.55 seconds. And so that's the time value put into that equation. So it's the same equation, but we have put in different times based on when these stones were dropped. So the first one has only traveled 7.6 meters. So that extra second is making a large difference. So what we're ending up with here then is a delta H of 27.3 meters is what we have. Okay, the numbers seem pretty good. I'm a little concerned about this one here, but no, that probably seems right. So that extra second of drop is making quite a significant difference, and that's the acceleration effect. So you keep traveling larger and larger. So they're going to continue to separate. Not only did the first stone get a head start in terms of distance, but that first stone got a head start in terms of velocity. So it's out ahead of the second stone after 1 second. It's out ahead of the second stone by 4.9 meters, and it's also traveling. After 1 second, it's traveling at 9.8 meters per second. So it's got that velocity head start as well. So the distance should keep increasing. All right, so that's problem 1. Any questions on that? Let's go ahead and move into problem 2. Now this looks kind of like a chapter 4 problem. This one is going to involve forces. We got to get some force diagrams set up. Let's take a look at a solution for this one. And as always, remember for many of these problems, for most of the problems, there are going to be variations in how we can go in and solve things. And so even when I'm, if I'm writing up solutions to some of these, I may take a certain approach or I may take a different approach. So we'll try and talk about those as we go along. So for this problem, this is kind of representing stuff from chapter 4. And of course, one of the first things that we want to make sure you've really developed is being able to draw these free body diagrams or force diagrams. So that means that for this, for these two objects here, we need to label them. I label them as M1 and M2. Now there's a tension in the string on both sides. I guess this is probably a good way to look at them. M1, M2. I'm going to go ahead and say M1 is the larger mass. And so that would be at 0.500 kilograms and 0.300. Notice the units conversions along the way. So I think what you're going to find is a number of these problems have units conversion built into them. So be ready to move back and forth between different units. We've got the masses identified. It's the gravitational field of the Earth that's creating these gravitational forces. Now, and I do have the acceleration going the wrong way, so I got to go back and get that arrow switched. So that arrow is back the other direction. Let me get that changed in the notes. So I'm going to go with these two diagrams here. I'm going to say there's an acceleration here. M1's larger, there's an acceleration here. Now, the standard formula that we always come back to is acceleration is determined by the net force divided by the mass. So for object 1, the acceleration is in the direction of m1g, so that gets the plus sign. But the acceleration we've drawn is opposite t, so t is holding things back. So we'll write this as m1g minus t. And then what we have to do once we get the net force is divide through by the inertia of the object, its inertial mass. So that's going to get divided by m1. So the formula we wrote here is net force divided by mass. Now for object 2, very same thing, net force divided by mass. But since this has the acceleration drawn in the correct direction, this way, this time it's t in the direction of the acceleration. So kind of the approach we're taking here is when we write these formulas down, the intention is that the masses are positive, g is a positive number, t is a positive number. We put the minus signs in by hand. So by putting the minus signs in by hand, it's following the approach of avoid hidden minus signs. If possible, I want to have all of the symbols representing positive numbers, and I want to be able to put the minus signs in by hand. And so that's what we've done. Here is our fundamental formula for object 1, and here is our acceleration force formula for object 2. Now, below those, what I've done is I've rewritten each one in terms of tension. So I've solved that for tension, and I've solved this one for tension. And we've seen examples like this in lectures. What that's going to allow us to do then is I can take this expression right here. So I can take this expression and set it equal to this one. Since these are both t, the very same t, then I can take these expressions and set them equal to each other. Now, as we've been talking about, we're not going to be able to include rotating objects until chapter 10. So in chapters 10 and 11, we'll look at rotational motion. We'll learn how to take the pulley into account. But for now, what we say is the pulley is, it should really say that in the problem too. The pulley's mass can be neglected. All right. For now, you can assume that on all the problems. Unless stated otherwise, the pulley's masses are just being neglected. So, and that we'll see in chapter 10 that works. If we assume that there's no friction in the hub, you know, the axle where the rotating object is rotating, no friction there. Of course, there is friction along the edge here. So as this drops, the string pulls the pulley. So the pulley is going into rotation. But if it has a really, really low mass, it doesn't have, has a very small effect, a negligible effect. All right, so I'm going to take these expressions, set them equal to each other, and then we bring all of the acceleration terms to one side and factor out the acceleration. I'm taking all the remaining terms to the other side, and what I can see is the terms on the other side are the two gravitational forces. M1g and M2g are what are showing up on the other side. And then finally solving for the acceleration here. Now, I like this form because we've solved for the acceleration. That's what they ask us to do in part B. So I'm not sure if I was clear about that. We're doing part B at this point. We have the force diagrams drawn correctly here. We have the force diagrams drawn correctly here, except I got that arrow backwards. That arrow needs to change. And then in part B, we've done some algebra, and we've solved for the acceleration. Now what I can do is I can take the difference between the two masses, 0.20 kilograms, multiply that by a common factor of g, and then I guess I need a parenthesis here too, and then add these two masses together. To combine, they'll be 0.800. So this is giving me an acceleration, 2.45 meters per second squared. That's what they wanted. And then the direction of those accelerations are shown on my force diagrams. Finally, in part C, it says, what's the tension? You know, solve for the tension in the string. Now, again, since the pulley is being considered to be massless, we can show that the tension on one side is equal. We can set the two tensions equal to each other. So there's really just one tension value to solve for. That's an important first step, because a lot of times students are trying to solve for two different tension values. And again, so far with these negligible mass pulleys, the tensions are going to be the same. So there's really just one t that I have to solve for. Now, I've got two equations right here that have tension. What I could do is this. I could solve using this equation. I could solve using this equation, and then I could check my answers. If I've done everything correctly, those two t values will match. Now, I kind of like that approach. I like being able to double check my results. Another possibility would be this. I have two expressions for acceleration here. So I could take this expression and this one, and I could set them equal to each other algebraically and solve for t. That also works. So there's kind of these, at least two different approaches we could take at this point. I'm going to go ahead and just plug into these equations. So I'm going to imagine I'm in midterm mode. I'm taking the midterm. If I'm taking the midterm, then I want to take maybe whichever approach is a little faster. And so I'm going to take these two equations. I did that. I plugged numbers in, and I ended up with 3.68 newtons for each of these. So the numbers that I ended up with worked out, they checked. So I ended up with the same number on each one of those. Okay, and as always, check the answers, see if they kind of make sense. And so you can see I'm always, when I look at my final results, I'm going back and taking a look at them and thinking, yeah, I have half a kilogram. Okay. Sure, why not? So, okay, yeah, it seems reasonable. All right, so those are the numbers that we have. Now, as always, if you guys catch errors in any of my notes that I'm providing, let me know right away, and then I can make those corrections. I can send out announcements to the rest of the class, and let them know that we need to update the solutions that we have. All right, that's problem 2. Again, these are good problems. I feel like in preparation, these are problems that have shown up on midterms. Kind of gives you a feel for what a set of problems on the midterm are going to be like. All right, I'm going to jump ahead to problem 3. Here we've got a car. Mass is 1,100 kilograms. Velocity 30 meters per second. So I'm writing everything down. Here is my diagram. And in fact, yeah, part A says draw a diagram of the car and show all the forces acting on it. So I have a car that's slowing down. It's putting on the brakes. And so the velocity is to the right, but the acceleration is going to be to the left. The acceleration is going to be opposite the direction of the velocity. So now the forces acting on the car, there's going to be a gravitational force downwards, mg. There's going to be a normal force upwards, n. There's going to be a frictional force. And the frictional force is going to be opposite the velocity. The frictional force is creating the slowdown. It's creating the acceleration. And so the force is opposite to the direction the car is traveling. That says there'll be an acceleration in that direction, and that's going to bring down the velocity. Now, we're just going to stop the car, and then the problem is over. So once we have reached v equals 0, then the acceleration stops, okay, or the deceleration stops, and end of problem. Now it says that we want to calculate for particular coefficients of friction. We want to calculate how much distance it will require to stop the car. Now the coefficients of friction, they're not that good. Car tires are supposed to be much better than this. It's saying that if there's a kinetic coefficient of friction, that would mean if we lock the brakes, so if we slam on the brakes and we lock them and skid along the surface of the pavement, the coefficient of friction for that sliding or kinetic coefficient would be 0.30. Now, if we use the brakes properly, which means we put the brakes on right up to where we're using near the maximum coefficient, well, the maximum static friction, which would say, let's use the coefficient of static friction, 0.45. That should slow us down better than trying to slide to a stop. So K is for kinetic coefficient. That means the surfaces are sliding past each other. S is for static. That means that the wheels are rolling so that as the wheels come down, there's no sliding. And that actually allows us to stop the car in a shorter distance, and it allows us to control the car better. If I'm using static friction, I can continue to turn the car left or right. Once I've gone into a skid, I really don't have control over the steering. So in part B, they're saying, okay, let's slam on the brakes and use kinetic friction and see what happens. Now, automobiles, for many years now, I think all automobiles have anti-lock braking system, which means the braking system is built so if sensors detect that your wheels have stopped rotating, the car automatically lets up on the brakes until you regain that static friction control. In any case, so here's the acceleration. Now, I want to represent the direction of the acceleration. Now, I could do it entirely from the diagram, or I could start putting minus signs in. Either approach will work. And so, if you're taking a midterm and you want to just make a quick comment, that's fine as to how you're managing your plus and minus signs on this. Now, what I did is I did kind of a hybrid. First, I said the acceleration is due to the frictional force divided by m. So that's coming back to force divided by mass will determine the acceleration. That's what will determine what the acceleration is. And then I did go ahead and put a minus sign in. So I put minus mu times n. Now if this is skidding, then I'm looking at mu sub k. So mu times n, and then from the diagram I can see n and mg are the same value. So the value of n will match the value of mg, and so I can substitute for n and put in mg, and then the m's cancel. So the inertial mass and the gravitational mass cancel out, and it says that the acceleration then is independent of the mass of the car. What it really depends on is the coefficient of friction. So I'll say minus mu sub k times g. Now, I plug those numbers in, and it says that if I'm sliding across the pavement, the acceleration will be minus 2.94 meters per second squared. Now again, they're not very high numbers. Maybe it's raining, and the surface is kind of slippery right now, and that would make it easier to go into a skid in any case. Now what I'm going to do is I'm going to come back and look at equations for constant acceleration. So we're assuming the frictional force is constant, and that will give us a constant acceleration, and that constant value is given by mu sub k times g, and the value is 2.94 meters per second squared. Now, I went ahead and did this, which was, I put a minus sign in here by hand. So with this minus sign here, I'm really just thinking in terms of absolute value of the 2.94. So eventually the velocity will be 0. So when the velocity is 0, what will the value of d be equal to? And so that worked out to be v naught squared over 2a. Now since I put the minus sign in here, I don't need the minus sign from here anymore. I've dropped it. And I'm just writing this as v squared over 2a. So 30 meters per second was the initial velocity. I square that, divided by 2. 2.94 is the acceleration, meters per second squared. And let's check out the units, right? Because the units have to work properly. And so I've got meters squared divided by meters. That leaves me 1 unit of meters. Now that's a distance. That seems correct. Seconds squared here actually will cancel seconds squared. So the seconds are all gone. And that sounds very good. So the seconds completely canceled out. The meters did not. I have 1 extra factor of meters. So my answer will be in meters. And that's a distance, and that's very good. Putting the numbers in, wow, 153 meters. Yeah, it's a slippery surface. So we've got a really slippery surface, and we're just sliding across that. We've locked the brakes, 153 meters. 30 meters per second, let's see, we're going pretty fast. So 30 meters per second was what, like 67 miles an hour, something like that. So it's freeway speeds that we're looking at here. But 153 meters is a good distance. All right, what if we stop the correct way, where we allow the wheels to keep rotating as we put the brakes on? So that will use static frictional forces. Well, everything is the same. So the force diagram is the same. The constant acceleration formulas will be the same. Everything will be done the same, except the coefficient of friction will be different. And again, the masses cancel out. So what did they tell us about the car? Ooh, they said it's an 1,100 kilogram car. And sometimes students go, well, it wasn't a fair problem because you never use the 1,100 kilograms, and you don't have to use all the information given. Okay, so to make the problems more realistic, there could be information in the problem that you don't use. You know, in the real world, no one walks up to you and tells you, all right, use this number and this, but don't use that number. You know, in the real world, you have to decide which numbers are relevant and which ones are not. So that's, you know, that's part of the problem, is deciding what to use. All right, so when we put in the different coefficient, again, the static coefficient is better, but it's not hugely better. The same formula applies here. We can do v naught squared over 2 times the acceleration. This time the acceleration will be a bit larger. So I kind of changed the signs here mid-problem. So this time I didn't bother with the minus sign here. I decided I preferred just using the minus sign from here. So the amount of acceleration, 4.41, and then from the diagram I can see it's in the negative direction relative to the velocity. And plugging those numbers in, I'm now stopping the car in 102 meters instead of 153. All right, questions on that? So again, I think this is a pretty representative type problem. All of these so far I'm thinking are really good. Let's move on to this last one on this page. Now we have a second page. So this is one set of problems, and then we'll take a break, and then we'll come back and we'll do another set of problems, another complete midterm 1, again from a previous semester. So here's problem 4, and it says whether communication satellites, we got to spell satellites correctly, so that could be corrected too, are often placed in geosynchronous orbits. It's funny how when I proofread these, I guess I have to slow down and proofread them. Anyway, whether communication satellites are often placed, I don't pick up these things a lot of times until we're here in class. So geosynchronous orbits with periods equal to the rotational period of the Earth. Draw a diagram showing the motion of a geosynchronous satellite and the forces acting on it. So here is Earth. I put a big M for the mass. And here is the satellite. Put a little m for the satellite. We've been looking exclusively at circular orbits. So let's use a circular orbit for this. This would be the direction of velocity at a given instant. This is the direction of the acceleration. We looked at this with circular motion. So now we're into, chapters 5 and 6, looking at gravitational forces and looking at circular motion. So now for circular motion, we had worked from a couple different formulas that would tell us how the acceleration was related to the radius of the circular motion, the velocity of the object, or what we found was instead of using velocity, we could write the acceleration in terms of period. And this problem seems like a perfect example of where we could work in terms of period instead of in terms of velocity. So if you remember, we talked about in class that the Earth's rotational period actually isn't 24 hours. It's 23 hours and almost exactly 23 hours and 56 minutes. So I'm going to go ahead and use that, 86,160 seconds. And that has to do with when the Earth rotates, it's also moving in its orbit. And because of the orbital motion, our clocks, the way that we work with time, is based on where the sun is in the sky. So Earth has to do a little bit more than one rotation each day to face the sun, and that's where the extra 4 minutes is from. So if we go back and think in terms of the time it takes for Earth to actually make one rotation, this is the number. Now, if you use 24 hours, I don't think that's a problem, I'm going to say. At the most, I would take off 1 point. Because I do think that's an interesting piece of information that you can carry away from the course. In any case, they wanted the diagram. I drew the diagram. I identified the force. Now, the top formulas, those are kinematics. So that's just saying how the motion is related, how the V's and the R's and the A's and the periods are all related. This is Newton's laws of motion, saying that any acceleration, if it's circular motion, that formula still applies. So it's going to come from looking at what force there is creating the acceleration and divide that through by the mass. Now, what we've learned in chapter 6 is that in general, the gravitational force can be written as big G, big M, little m, divided by distance squared. And that distance is center to center. So remember, this is circular motion. R is the radius of the circle. That's the little r here. And then there's another little r, and that's from the center out to the object. Now it turns out that the radius of the circular motion and the distance between the two objects, center to center, are the same thing. So we don't have to use two different variables. We can use little r for both. But there is a distinction here. This is a distance, center to center, between the two objects. That is the radius of the circular motion. So this is the formula for gravity, and the little m's cancel, which says that the acceleration of the satellite depends on the mass of the Earth, but it doesn't depend on the mass of the satellite itself. So that canceled out. Now I can take this formula and I'm going to use this kinematics formula and set those two equal. Now, we wrote down what the period is going to be, so I can take this formula and start solving. In part B, they are asking what would the r value be? What would the radius of this orbit need to be? Let's see how they... we are on to... let's take a look at this. We are on to chapter 4, weather and communication. Yeah, what is the radius of the orbit? the orbits of these geosynchronous satellites. So I'm taking that problem and just solving it. R to the third is big G, big M, period squared over 4 pi squared. Now here is big G, 6.67, 10 to the minus 11, newtons, meters squared per kilogram squared. Check the units at each step. So here are the units. Here's the mass of the Earth. Did they give that to us? They did. Notice, here's another example. See the Earth's radius over there? I don't think that's going to play into this. The Earth's radius is not going to have an effect on the gravitational force. It's just the results on the mass. Now, also, we don't need the Earth's radius to measure r, because the distances are measured center to center. So that Earth radius, you know, that's a comparison number, and let's see how it gets compared here. Putting that in mass of the Earth, period squared, divided by 4. So there's no units in the denominator. Ooh, let's see what units are here. I've got newtons. Now newtons have kilograms, meters, divided by seconds squared. So kilograms, kilograms, all the kilograms go away. I'm going to have per second squared, those will cancel the seconds. So the kilograms are gone, the seconds are gone, all that's left are meters. How many factors of meters do we have? And I've got 2 factors here, and 1 from newtons. That's 3 factors of meters. I am going to be taking a cube root, and that'll reduce it down to meters. So the units do check out. And the number I ended up with was 42,100 kilometers. And what I want to do is I want to compare that with the radius of the Earth. Now they didn't ask about that, I'm just curious. And so that's like 6 or 7 Earth radiuses, right? These are a good distance from the Earth. So 2, 3, 4, 5. I didn't scale it too bad. It's probably to scale, I should have put the satellite out a little farther, but those satellites are way up there. Okay, they are a good distance away from Earth, but Earth is still the dominant central gravitational effect for the satellites. So they maintain that orbit. And then as far as V, in part C, they want to know how fast. So we want to launch these, turn the rocket so it's right along that circular orbit, and then we want to get the satellite at exactly the right speed, and then turn off the rocket engines, right, and let the satellite go into orbit. It's in orbit at that point. So 2 pi r is the circumference, divided by the period, putting all these numbers in, that's r, there's the period. It says that these satellites would need to be traveling at 3,100 meters per second. So it's still a pretty good speed, right? Yeah, that these satellites are traveling at. All right, again, let's see, a good problem in kinematics from chapter 2, a good force and acceleration problem from chapter 4. Here is a frictional force problem from chapter 5, and then weather and communication, satellite in orbit from chapters 5 and 6. So that's a pretty good representation. We don't expect any problems to be exclusively from chapter 1. Some of the things we learn, like units conversions and such, are just going to show up in the other chapters. So yeah, that's a pretty good representation. So let's take a break. So I'm going to stop there, and we can take a break. We'll come back and look at another set of problems from another midterm.